All right, looks like we can get started here. Hello, everyone, and welcome to the High Voltage Seminar. This is the Troubleshooting Gate Drive Circuits in Automotive and Industrial Applications session, being presented by Mamadou Diallo, an Applications Engineer from the Gate Drivers team. My name's Tristan Foro. I'm a Product Marketing Engineer for the Gate Drivers, and I'll be the moderator for today's session. All participants are muted for the session, so please use the chat function to ask any questions, and we will be answering some questions in chat and saving some Q&A for the end. Also, please chat us if you're having any problems hearing or seeing the presentation. We have a very interactive session planned for today, so be on the lookout for polls on the right side of your WebEx. And with that, I'll hand it off to Mamadou to get started.
Thank you, Tristan. Hello and welcome everyone. My name is Mamadou Diallo. I'm an application engineer with the High Power Drivers Group. This presentation will discuss pitfalls related to gate drive circuits in automotive and industrial applications, specifically gate driver biasing, bootstrap supply, and its components necessary to generate high side bias. I will also discuss the effect of open functional pins and the impact of DVDT noise in gate drive circuit. I will then identify parasitics and finally show issues related to poor layout and how to correct them. The part numbers mentioned in this presentation will include the 620 volt half-bridge gate drivers with interlock UCC 27710, the 120 volt half-bridge gate drivers with integrated boot diode UCC 27201 and UCC 27282, and the dual channel low side gate driver UCC 27524. The topologies I will discuss today are relevant to motor drives, switch mode power supply, as well as solar inverters applications. This presentation is meant to be interactive, so for each issue, I will show some waveforms and schematic. Then I will start the polling to give you a chance to identify the problem and possible root causes before I finally share the answer. Before we get started though, here's a quick background on gate drivers. Where do we find gate drivers? Applications for gate drivers are very wide, and I name a few here, like battery management system for portable devices and its adapters, server, telecom, UPS, EV charger, motor drives, as well as Class D audio, appliances and kitchen, renewables, and solid-state lighting. Generally speaking, gate drivers have been used everywhere for efficient power conversion. And a quick background here, modern power electronics are dominated by switch mode power conversion. Commonly used devices for power switching are MOSFETs and IGBTs, and these have two states, on and off, controlled by a gate terminal. The gate terminal controls the on and off state of the transistor. VGS equals voltage between gate and source. To turn on the transistor, simply apply a positive VGS voltage greater than the specified threshold. To turn it off, VGS must be lower than the threshold level. The gate capacitance is a capacitive, the gate terminal is a capacitive input, high impedance terminal. There are two parasitic capacitors to be aware of inside the MOSFET internal structure, that is CGS and CGD. All right, let's get started on our first issue here. Closely look at the waveform and schematic provided. This is a typical half-bridge configuration where a PWM signal is controlling the driver's input. The bootstrap circuitry composed of C-bias on the VCC pin, the bootstrap cap or HBHS capacitor, and the boot diode. These bootstrap network components generate the bias for the Q1 FET on the high side, and this high side FET is referenced by design to the switch node HS. The driver's low side output LO buffers the PWM signal to the Q2 FET reference to ground. What could be wrong with the VCC supply? What could be causing this issue? I'll go ahead and open up a poll here and give you a chance to discuss or identify possible root causes. There we go. I have the poll going. I'll give it about 15 seconds. Okay, let's see. Looks like we have most of you guys picking both B and C, and which is the high ripple due to insufficient filtering on the VCC. That makes sense. That's a good answer. And also C boot and C bias incorrectly sized. That's also a correct answer. Notice on the schematic here, essentially C bias equals C boot, also equal to 1 microfarad each. This situation may cause very high ripple on the VCC supply, leading to driver malfunction, as shown on the waveform where HO and LO are simultaneously switching, potentially causing shoot-through. As it is, the bias cap is not correctly sized to allow capacitance shift occurring from DC bias and temperature variations. This can lead to UVLO tripping if the ripple on the VCC reaches the UVLO threshold and disable the gate driver. Another result from this issue is the circuit being susceptible for EMI noise. Excellent. Now, how do we address this issue? We address this issue, as we pointed out, by correctly sizing the bias capacitor. The charge to replenish the bootstrap capacitor must come from the VCC bypass capacitor. As a general rule of thumb, C bias should be sized to be at least 10 times larger than that of the boot cap so that it's not completely drained during the charging time of the bootstrap capacitor. This allows the bootstrap capacitor to be properly replenished during the charging sequence. This 10x ratio results in 10% maximum ripple on the VCC capacitor in worst case conditions. An alternate method to determine the C bias is also included in the bottom right corner. It consists of determining the maximum desired ripple on the HP supply delta HB, knowing the supply voltage of the gate driver IC, the bootstrap diode forward voltage drop found in the data sheets of the diode, and the HP pin UVLO threshold found in the gate driver data sheet. From there, the minimum allowed bootstrap capacitor is determined through the ratio of the total gate charge and delta HB. The maximum value for this cap will vary by application. And from there, you can size the VCC capacitor to be 10 times that of the bootstrap capacitor. On to our next issue here. This next issue shows another waveform of a half-bridge configuration where channel 1 in yellow is the high side input, channel 2, the switch node in red, channel 3 in blue is the low side output, and channel 4 captures the high side output HO. What could be wrong with the HO waveform? Please take a moment to think of an answer. I'll go ahead and open up the poll here. There we go. All right, let's see here. And I'll share the results of the poll here. Looks like we have 11% on picking option C, which is correct. The significant voltage drop on HO. That's absolutely correct. Notice the leakage occurring on the high side gate channel 4 on the green waveform. This HO leakage can be caused by a combination of many factors, including low boot cap values not capable of storing the required energy to drive the high side FET. Another common reason for this may be related to low gate to source resistance on the high side. And the third probable cause for this might be switching at very low switching frequencies. All of these causes could be leading to heating across the junction terminals of the MOSFET, as well as ripple on the output. Simple ways to address this problem is essentially increasing the bootstrap capacitor in order to provide the required bias for the high side gate. Increasing the gate to source resistor also helps this issue. After implementing these changes, it is critical to maintain the HVHS capacitor very close to the driver's HVHS pins. Shown on the bottom right corner is how to correctly size the HVHS capacitor again, knowing the power transistor's total gate charge and the maximum allowed voltage ripple. Similar to the first section, depending on application, one may approximately size the HVHS capacitor to be 10 times that of the gate to source capacitance. All right, our next issue, still dealing with bias supply around gate drivers. We still have the same topology from the previous example. Channel 1, the yellow waveform, captures the HB to VSS voltage. Channel 2, the blue waveform, shows the HO to VSS signal. And channel 3 captures the HS switch node in pink. Do you see anything wrong with the waveform? What could be causing this? I'll open up another poll here again. There we go. Okay, let's see here. I'll go ahead and close the poll and share the results. It looks like we have 15% of you guys identifying the large duty cycle on HO. That's absolutely correct. And channel B, option B here is not the case. If you noticed, channel 2 is the HO to VSS, which has very high duty cycle, which essentially means that the low side has very low on time. So what this essentially means is that during the low side on time, during which the HVHS capacitor charges, you don't have sufficient time to essentially fully charge the HVHS gap. As you see on the waveforms, during some pulses, the HS signal is switching very close to ground, while others are limited to 15, 18 volt. This is again related to the HVHS capacitor not fully charging during the low side on time. Keep in mind that the bootstrap capacitor must be allowed to fully replenish every time that the low side FET is on. As it is right now, the low side transistor on time is too short due to the long duty cycle on the high side and preventing the switch node from switching to ground. The minimum bottom FET on time is determined but such that it is greater than T equals CHVHS times R, R being the bootstrap resistor. One possible solution to this issue is to reduce the bootstrap resistor value in order to allow peak currents from the bias supply to quickly charge the HVHS capacitor. This time constant may be tuned to achieve the desired startup time. Another solution to this problem is also to ensure sufficient minimum on time for the low side switch, which will allow the HS to switch close to ground for the HPHS charging currents to have a path to ground. In this next issue, we have another half-bridge topology. On the right, the waveform captured where channel 1 in yellow is looking at the HPVSS signal, and channel 3 in pink captures the low side output LO. Can you spot the problem here based on the waveform shown? Allow me to open up another poll here. I'll give it about another 10 seconds or so. Okay, let's see here. All right, looks like the majority picked option C, ringing on HPVSS, which is absolutely correct. Option D is also a good answer. Noise and oscillations likely caused by fast HS slew rate. So both C and B are appropriate here. And what's essentially happening here is the long duty cycle on the LO channel. If you noticed, this is causing overcharging on the bootstrap capacitor through the red path highlighted that I'm showing right now. In this case, the on time of the low side output LO lasts well above 500 microseconds. Notice that this is the opposite scenario from the previous slides that I just shared. That is creating overcharging on the HPHS capacitor, which as a result is causing oscillations, overshoot on the HP node shown in yellow by channel 1. This overshoot and ringing reaches almost 40 volt, which is well above the HPHS ABS max of most modern drivers. One way to remedy this issue is to increase the HPHS capacitance value, allowing to increase energy storage capability of the capacitor. An alternate way to increase to resolve this issue is to increase this resistor from the bootstrap network, allowing to reduce peak currents charging the HVHS network, and therefore increasing the time constant RC to charge the HVHS capacitor. This time constant occurring during the high side off time or low side on time explains the duty cycle dependency of these applications. All right, here's another issue where we have, again, another half bridge, and we're still looking at biasing issues around the gate drivers. On the waveform to the right, I'm showing the HVHS supply, which is enabled, captured by VC boot in blue. The driver is also enabled as shown by channel 1, the yellow waveform. The PWM inputs, HI and LI, are both on as well. The pink curve on the waveform shows the low side output switching normally, but somehow the high side output is flat, stuck at 0 volt, and no switching occurring as shown by the green curve. What could be causing this issue and why? I'll go ahead and open up another poll here. Here we go. You have a little bit more time here. I'll probably give it 25 to 20 seconds or so. Okay, let's see. Looks like we have 27% of the responses selecting option B, which is insufficient VC boot voltage, which for this case, I can see where that's coming from, but for this case, not so much. Really, if you notice here, look at the LO channel, for example. This is switching right away because we already have sufficient bias above the UVLO threshold. Notice that the input, the LO input is enabled well before the HVHS supplied reached the UVLO rising threshold. This design did not take into account the UVLO delay occurring during power up, leading to skipped pulses or missing pulses. We can see the HO pulses switching 50 microseconds later after the supply has reached the UVLO rising threshold. This UVLO delay is dependent on the driver and must be accounted for in all applications. So essentially, the driver had sufficient bias, but because they did not synchronize the inputs, the HO channel has a UVLO delay, which is approximately 50 for this specific case. Some drivers may have lower, but you want to make sure that you synchronize your PWM signal well after the supply has crossed the threshold. So before the driver is ready to deliver proper output state, there is a power up delay from the UVLO rising edge to output. This delay varies according to the driver. This may be as high as 50 microseconds for some drivers. It is therefore recommended to consider proper margin before launching the PWM signal. The figures on the right show power up UVLO delay timing diagram for input and VDD supply. It is necessary to synchronize the input signals only after the bias supplies are both ready. This example shows sufficient margin where the PWM signal are launched well after the driver supply has crossed the UVLO threshold. On to our next issue here. So we have another half-bridge topology again, similar to the previous examples. In this case, we're using an isolated gate driver. Channel 1 shows the PWM input in A. Channel 2 captures the out A, while channel 3 in red captures the switch node HS signal, and channel 4, the inductor current in a DC-DC step-down converter applications. Do you see anything wrong with the waveform? What could be causing this here? And while you think about that, I'll go ahead and pull up another poll here. There we go. And we'll give it about another 20 seconds or so to give you a chance. Okay, let's see here. All right, looks like we have both option B, 9% of you guys with non-optimized layout. Yes, that's true. That could be a possible cause. Also, noise on input from either DI/DT from the power stage or ground bounce from the power stage as well. So both B and C are really good options here. So essentially, what you're seeing on these waveforms is the noise on the PWM signals, which is coupling to the power stage, causing severe overshoot across the system. During high-frequency switching applications, it is also common to encounter ground bounce. due to high DVDT and high DIDT from the power stage. This factor, combined with poor layout, could cause noisy signals on the driver's input and controller, which will couple throughout the gate drive portion. It is typically recommended that users avoid shaping the input signal of the driver IC, but for this specific case, it is better to have a small RC filter to mitigate the ringing caused by the non-optimized layout and the very high DIDTs. Such a filter may use resistor values as high as 100 ohm on the input and capacitor values as high as 100 buff. All right, here's another issue. So now we're transitioning away from biasing supplies and looking at a different common issue. We still have a half bridge two half bridges in a full bridge topology now, where we're capturing the voltage across VAB, where channel 1 shows the VAB voltage across the 2 switch nodes, and channel 2 captures the phase current. What could be causing the glitch on VAB voltage? I will open up the poll here. Though there's several things that could be causing this issue specifically, I'm giving you a hint with the pin with high Z on the top left here. Allow me to open up the poll here real quick. There we go. Okay, let's see here. All right. It looks like some of you guys picked noise coupling from the gate drive portion. Yes, that could be a possible root cause. And signals on the driver's input may be beyond ABS max. That could also be a factor, though option A will likely damage the driver altogether. And so for this specific case, we encountered this commonly with applications where functional pins are left floating. So in this case, you notice the glitch on the VAB voltage, which may be traced back to one of the driver's channel's increased propagation delays. In this scenario specifically, in A to out A is being delayed by 1.2 microseconds, well above the typical specification of 50 nanoseconds. This delay is seen down at the full bridge, causing the glitch of the power stage captured by channel 1. So typically, we recommend essentially not leaving any functional pins floating, which may cause noise coupling into the driver IC. The specific case shows the dead time pin left floating when it should be either tied to an external resistor for dead time setting or tied to VCC to allow overlap of the 2 channels. The functional pins should never be left floating when unused, including input pins, which should be tied to ground when that specific channel is not in use. All right, now we're going to go into our next phase, dealing with parasitics in the gate drive portion. If you notice previously, we started with the bias supply. We discussed biasing on the VCC supply. We also discussed biasing on the HBHS capacitor or bootstrap capacitor. Then we also looked at leaving functional pins open and how they impact the gate drive portion. Now we're going to look at parasitics, specifically junction capacitance, PCB traces, wire bond inductance, and resistance, which are all parasitics in the gate drive portion. Therefore, the turn on and turn off will be a little bit more complicated. For silicon carbide FETs and silicon MOSFETs, there is a body diode also considered as parasitics. Back to our typical half-bridge topology from the previous examples, we have a low side channel in green captured and the switch node HS voltage and the high side channel HO. In this case, assume that all the biasing are within normal ranges and that the PWMs are also within the recommended operating conditions. What could be wrong when HO is turning off, considering parasitics in the gate drive portion? I'll go ahead and open up a poll here while you think of an answer. Here we go. Okay, let's see here. Okay. Here's the answers. Looks like 23% of you guys picked option C, overshoot on the HS pin, which is absolutely correct. And also option B is false logic on LO. If you notice, LO initially goes high and then essentially saturates back to 0 volts, whereas the HO, when HO is turning off, you notice the HS also overshooting up to the gate drive voltage range. And this is commonly associated to parasitics in the gate drive portion, specifically high DVDT on the high side, HO, which, if coupled with high DI/DT through the transistor, may cause parasitic currents at the gate through the CGD capacitor. This parasitic current, coupled with the gate resistor, may develop a gate voltage which could turn on the low side transistor if this voltage is above the VGS threshold. To address this issue, it is recommended to use a gate to source resistor, which will allow the gate to be pulled low while also providing a path for the parasitic CGD current to ground away from the driver IC's output. Another way to address this issue is also Miller clamp, a driver with Miller clamp, which may provide a low impedance path to to sink the parasitic current away from the driver's output. All right, here's another scenario where we're looking at a parasitic still. In this scenario, we have the gate to source voltage oscillating shortly after the initial pull-up. Consider this case as another half-bridge topology. Why is the gate voltage oscillating? What could be causing this oscillation? Please take a moment to think of a possible root cause here. And I'll open up this poll here to give you a chance. All right, there you go. Okay, let's see. Looks like we have Majority of the answers pick in option C, which is the closest answer here, and I'll widen this up here. Option C, large inrush current due to the long reverse recovery times of the MOSFET body diode. That's absolutely correct. Also high DI/dt as well. So the better option here is B and C combined, which for this case is essentially showing how very high DI/dt can couple back to the gate of the transistors. So what's happening essentially is under hard switching applications, the body diode reverse recovery will occur. The critical waveform is shown in the top middle here. This reverse recovery current will be reflected at the top switch and generating more turn-on losses. With two experiment results for body diode of MOSFET and anti-parallel diode of IGBTs, you could see tremendous amount of inrush current, which is caused by the reverse recovery. The driver IC will typically overshoot in this scenario or cause EMI issues as well as ringing. For silicon MOSFET, the overshoot could be over 5 times that of a nominal switching current, while IGBTs have relatively smaller overshoot amplitudes. The main reason is the body diode, again, considered a parasitic diode and not really optimized for the reverse recovery times in hard switching applications. So a quick way to address this is really implementing ZVS or zero voltage switching to prevent conduction losses on the body diode. And if you see here, you want to make sure that you're slowing down the body diode reverse recovery and using a robust FET with an optimized QRR body diode. And also another alternative is implementing soft switching to prevent the body diode from conducting during these transitions. Minimizing the gate drive loops. So this is also common where a PCB layout can be detrimental to the gate drive portion, specifically the gate drive loop from the output stage to the gate resistor to the gate of the transistor. So when designing your gate drive path, you want to make sure that this loop is as minimized as possible. As shown on the left here, you see the gate very close to the driver's output and connected through short and wide PCB traces. The ground return trace use significant copper plane to help with thermals as well. On the right shows the schematic. This will essentially minimize any DI/dt and parasitic coupling in the gate drive loop. When using totem pole or BJT buffers for current boosting, you might want to place these as close as possible to the power transistors. And in most cases, the gate drive loop is always one of the leading causes of parasitics in gate drive applications, because this is typically the last part in the power stage where customers will focus on prioritizing the power stage rather than the gate drive portion itself. Here's an example of a bad layout where you have the biasing capacitance placed too far away from the VCC supply on the right, and on the left shows a correct placement of the CVDD capacitor directly across the IC. So typically, in addition to the capacitor placement, you want to make sure that these traces being used are as wide as possible to minimize stray inductance in the PCB gate drive loop. Additionally, you want to also prioritize the driver's output stage and the CVDD capacitor before finally placing the input stage components. So if you're designing a gate drive circuit, the priority is on the output stage, specifically HO, LO, the switch node, and then the ground return loop from the low side fed to the controllers, which is shown here, the CVDD capacitors, and at the very end, the input stage connecting to the MCU. All right, on the next slide here, we're showing a double pulse test on a bridge topology, where we're essentially showing, in this first case, a double pulse setup again, where the HO is, where the HO signal is applied, and what is essentially wrong with my HO output. I'll pause here for a second to give you a chance to think it through. Allow me to pull up this poll here. Okay. I'll move it over just a little bit. So again, this is a double pulse test commonly used for bridge topologies. The inductor current shown on channel 4. And while you guys responding there, let's see. Okay, let's see here. I'll go ahead and share this. As you see, there is a missing pulse on the HO channel, which is essentially not following the HI input or the PWM input. You expect the HO channel to have the same duration as the HI channel, but somehow the HO is able to go high briefly before essentially saturating or getting stuck low at 0 volt. So this is a case of a missing pulse in a double pulse configuration. And I'll share the reasons for this in a second. I'll give you another case here where it's the opposite, where we actually have a much longer duration. And I'll open up the poll for you here, and I'll share the root causes for this shortly. Yeah. So this is essentially the same setup. Somehow on the first one, you had a skipped pulse, and on this second setup here, you have a much longer duration pulse, which in both cases are not good. Okay, let's see here. So let's see here. Let's look at this waveform. So you guys selected option C. The HO pulse is too long. Yes, absolutely. So this is also considered a false logic. So essentially, the closest answer here is A and C. It's a false logic because the HO is not following commands from the HI signal, which is causing the HS spin or switch node to have a much longer duration as well. This can lead to significant damage or catastrophic damage in the power stage. And what essentially causes this is, and I didn't share this with you, I can zoom in here. What's causing this is really high DVDT on the switch node. Here's another example on case 3, and I'll give you another chance here before we go review all the answers with these 3 cases. Okay, let's see. see here. In this case, we also have, I'll give you a chance to think of an answer. Okay, let's see. So far we have option A, false logic. Yes, absolutely. A and C option, HO pulse is too long. For this case, not so much. The right answer here is a false logic. You expect the HO to saturate to the gate drive voltage. So once it pull ups here to the gate drive voltage, we expect it to be really high throughout and essentially falling off after the HI command is going low. There is a little bit of noise on the HI, but for this case, that is not the reason here. As you see, the HO has an intermittent turn off going high and low throughout the high pulse on the HI. Here's another waveform where HO is turning off intermittently again. I'll give you another chance here to review these. Okay. So in this case, you notice a different profile each time for the false logic or failures. In each case, you have different behaviors of the HO output, and what's going to happen is you'll see these different profiles and different failure rates, but essentially coming from the same critical issues, which is DVDT, essentially at the essence of it. Let's review what we have here. Again, false logic, yes, absolutely. What's happening in all three of these cases is really DVDT being the main issue. When you look at the switch node, a lot of drivers have specifically have a DVDT specified on the switch node. So when you have significant change in the voltage on that pin, it can essentially cause the driver to misbehave, to have false logic, to even cause catastrophic failure in some cases. For the previous cases here that I was showing, the CMTI or the DVDT on the switch node is as high as 285 volt, which is way too much for this driver specifically. And you will be rare to find a 285 volt nanosecond CMTI gate driver at this point, as of right now, today. And if you see here, what's happening is because the high side is referenced to the same switch node, exceeding the AVS max DVDT on that switch node will cause the high side switch or the high side channel to misbehave. Common ways to deal with this is essentially implementing a slower DVDT by increasing the turn on resistance. Also using ferrite beads with the same impedance as the gate resistors at the specific switching frequency also help. And other ways to mitigate this issue is through clamp diodes on the driver's output stage placed directly on the output pins. So you want to make sure that these are directly across the IC from switch node to the HVHS capacitance. So the key thing to remember from these is the switch node ringing and the switch node DVDT. You want to make sure you're slowing this down because not all drivers are rated at 200 volts per nanosecond. So it is a critical spec you want to watch out when using a specific gate driver IC or a half-bridge gate driver. The 0 volt switching previously mentioned is also another way to reduce the DVDT, which will prevent body diode losses on the low side. Here's another example of parasitics and DVDT caused by the PCB layout. Essentially, I want to make sure I emphasize here again the component placement and how the gate drive loop could derail the whole power stage and system. So minimizing the gate drive loop and also avoiding overlap between switch node plane, which is switching from 0 to 600 volt, and the logic voltages like the input stage, and also making sure that you have sufficient separation between that switch node and any other sensitive signals on the driver's side. This could create issues as parasitic coupling, as well as noise throughout the circuit. So with high slew rates on the inputs, with high slew rates on the switch node, the overlap of the ground plane and switch node might also inject noise in other circuit on the board. So it's really critical to have an optimized layout. We, as a team here, we are open to help customers design their power stages. We help them in terms of optimizing their layout and making sure that it is optimized to use the gate driver in a specific condition. And here's our 10th issue where I'm showing a waveform in a bridge topology. HO, as you know by now, is the high side gate, and LO is the low side gate. Do you see any issues with this waveform? Could this create any issues in a specific system? I'll go ahead and open up another poll here and see what you guys' responses are. Okay, let's see here. So far, it looks like we have overlap between high side and low side. Yes, absolutely. Possible shoot through. Yes. So in this case, both C and D are good options because shoot through is occurring when both HO and LO are overlapping, and this is a case where that could be an issue, essentially shorting these two transistors and damaging the FET as well as the driver IC. So this is critical to watch out for, and you will essentially cause excessive power dissipation across the bridge and damage those two FETs and the driver. You will also have false current tripping. That's a common issue. And you also want to make sure that you account for sufficient dead time between the high side and low side output because of variations on prop delays as well as variations on rise and fall times across temperature, across voltage. So all these things could certainly impact your gate drive voltage. Let's suppose you have, I'll go back to the previous slide here. Let's suppose you have a 2 nanosecond dead time, which is generally insufficient in any and most applications. And you have 2 nanosecond dead times, and you have a waveform like we're showing right now, where if I'm operating at 25C, I have some, let's say 21 nanosecond prop delay. Then I take my system to 100C, where there's actually 29 nanosecond prop delay, which essentially is going to potentially cause shoot through in my system. So you want to make sure that you account for the prop delay as well as delay matching variations across temperature, across voltage, and also account for the drive strength variations across temperature and bias as well. So it is critical to always account for any variance in temperature, bias, as well as prop delay variations, rise and fall times, and peak current ratings of the driver selected. So in summary, various issues are encountered in the gate drive portion. This is commonly related to either biasing supplies on the VDD pin or VCC, or also on the HPHS capacitor or the bootstrap network. Sizing these are critical to ensure that you're getting the best performance from your gate driver IC. Also, when using a gate driver in a half-bridge topology, you want to make sure that you're controlling the slew rate on your switch node, because the high side channel is referenced to that same switch node. So you want to make sure that you can control that with either a sufficient gate resistor accounted for, or making sure that your DVDT is within the driver specifications. At TI here, we have a wide range of gate drivers for every power transistor available. So for IGBTs, if you're driving MOSFETs or silicon carbide FETs for that matter, or GaN, we have the appropriate driver to help accomplish your gate drive needs. And in summary as well, the PCB layout plays a critical role. So it is therefore important to make sure that you plan accordingly by separating the power stage to the input stage signals, and also making sure that you have adequate component placement on the PCB layout. Having said that, I'll go ahead and open it up for questions and feedback and any concerns and questions.
One question we got in the chat is, what kind of online resources do we have for any additional questions after the session?
Thanks, Tristan. Any additional questions? We are available on ti.com, on E2E, e2e.ti.com, where we can address any specific questions. We also have that forum is available to any customer, where we will guarantee 24-hour response from the time you initially post. That is the quickest way to get a hold of us. Any other questions?
Yeah, if you guys have any other questions, feel free to share them in the chat. We'll leave some questioning open for a little bit to see if anyone has any questions. Yeah, Mamadou, we got another one. This one's basically, when should they use an isolated driver versus a non-isolated driver?
So when considering that, you want to make sure that it depends on your controller's placement on your system. So if you have the controller on the power stage, or if you have the controller on a separate board entirely, those are the key things determining whether you need a gate driver that's isolated or non-isolated. Let's suppose you have the controller on a separate board entirely. You could use an isolated driver to essentially provide that isolation. But if your controller is on the same board, is on the power stage, you do not need an isolated driver, and a standard 600 volt half reach gate driver is sufficient. And also, depending on your power transistor that you're using, you will need to determine which specific gate driver is adequate to be able to efficiently turn on that power transistor. So it all depends on where the component is placed, the MCU is placed.
Yeah, thanks, Mamadou. We got a few more questions. First, yeah, I'll share with everyone that the slides will be on ti.com afterwards. But to answer, there's a couple other questions coming in. One is, in some designs, the body diode of the low side driver will turn on. Does TI have anything to avoid the potential latch-up issues?
Can you repeat the question, please?
Yep. So in some driver designs, the body diode of the low side driver will turn on. Does TI have something to do to avoid the potential latch-up issues?
So a potential latch-up from a driver, you can essentially pick a driver with protection features that's going to protect the driver itself in those specific conditions. Now, you can also implement ZVS, zero voltage switching, to prevent the low side transistor FET from turning on. And this essentially minimizes any conduction losses through the body diode. So if you want to have a driver with protection features, we have those as well. But depending on the latch-up that you're going to need, we may have drivers with those protection features. But it all depends on the specific failure case or failure condition that you're seeing in your system.
Thanks, Mamadou. A couple more questions we have. Does the driver input need a termination when the control line is long? Example is a termination resistor at the end of the line between a microcontroller and driver needed.
Yeah, that's always good practice. We do recommend the termination resistor as well as placeholder RC filters on the input. In most extreme cases, I may sometimes recommend even a common mode choke when it's really, when you have significant noise. But for the most part, a pull down transistor on the input stage, as well as an RC filter, is typically adequate to protect the input stage. Usually 50K termination from input to ground is common. 50K up to 50K is generally enough to protect the driver.
Thanks, Mamadou. Another question we have, any particular considerations for the GaN drivers, like the LMG drivers?
The LMG drivers, the main considerations there are because of the high switching frequencies and the very low pulses, the most critical thing there is PCB layout, because of the narrow pulses that you're dealing with. Any small parasitics or a stray inductance in the gate drive loop will be amplified essentially. So a small overshoot can translate into very high parasitics in your system. And because of those systems being very sensitive in terms of narrow pulse width and having a clean signal, the PCB layout is the most critical thing. And to add to that, in addition to the PCB layout, I'd also suggest specifically delay matching, because you're looking at time of flight applications in some cases and radar, and you want to make sure that you get the consistent pulse out of the driver. So a GAN driver with consistent variations, let's say prop delay variations are stable through over VDD, over temperature. That's the second thing to watch out for with the GAN drivers.
Yeah, another question on Mamadou is basically how to use a driver with an internal diode in parallel with an external driver to load.
So I'm assuming here we're referring to internal diode as the internal bootstrap diode. If my assumption is correct on the question, you typically have, in some cases, some drivers come with an internal boot diode to help eliminate component size externally or save component size. So what you can do essentially is also place an external diode in parallel to essentially help share that power dissipation. So with the internal bootstrap diode, you have a trade-off essentially. So it's going to save you on component count, but it's also going to increase your thermal internally on the gate driver IC. So you can also use that external external bootstrap diode to help share that dissipation away from the internal diode.
Thanks, Mamadou. Another one we have is, what type of gate driver bias is recommended for such high DVDTs like you talked about today?
So there are several things in addition. Excuse me. There are several things in addition to the DVDT to choose a driver. Based on DVDT alone, you're not going to choose a driver. So the typical steps is, first, understand what type of FET do you have. If I have an IGBT, if I have a MOSFET or a GAN FET, how do I efficiently turn that on and off? The second step is, can my driver be powerful enough to efficiently turn on the gate capacitance? And you're looking at the current ratings. You're also looking at the prop delays. You're also looking at the rise time. Then you're also looking at, okay, now I have all that figured out. How do I know that my DVDT is sufficient for my application? So that starts with understanding how much DVDT you expect in your application. So knowing that DVDT, we can have, in addition to the other parameters listed, gate charge, total gate charge, your bus voltage, your expected operating range. Then we can help you select your driver, knowing the HS or switch node capability that we specify in our data sheets.
Yeah, and then a follow-up to that one, Mamadou. Any comments on the VDD bias related on the DVDT, like gate drive for GAN or silicon carbide?
Yeah, so for GAN specifically, because you're operating at really high switching frequencies, the GAN drivers will have lower gate drive voltage. So typically 5 volt is commonly seen with GAN topologies to help reduce the switching losses because of the increased switching frequencies here. So with the GAN drivers, you're switching essentially on the gate drive side 0 to 5 volts, and on the power stage you also have reverse recovery losses there, but it's not as 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 high as silicon MOSFETs, for example. Silicon carbide FETs, GaN, and IGBTs tend to have much faster reverse recovery losses on the body diode. So those have much less concerns. The main thing on GaN is really to have an optimized layout, which is critically important for this because again of that the narrow pulses, and how do you account as well for thermal, because you're switching at much higher switching frequencies. You're trying to get a very high power density, and so now the question is, how do you deal with thermals? How do you account for these thermals on your PCB board, which is also how the PCB layout can help with thermals by making sure you have an optimized and cooling system that will help you mitigate all these issues.
Yeah, Mamadou, I have another question that you might be familiar with. It's basically referenced in an isolated driver app note, but do you have any details, or can you explain a little more how to generate a negative bias with a single supply in a Zener diode?
That's a good question. I think you're referring to the UCC 21520 app note or data sheets. With
yeah,
that,
exactly.
I remember that. I think that's a little bit of a long answer, because you have the bias, you have the HVHS pin that you need to consider for one, and you also need to account for how do you pick the Zener diode to generate that sufficient bias or the negative bias to turn off the high side FET or low side FET. This is a little bit of a tricky scenario, because you want to make sure that you're sizing your negative voltage according to your actual needs. So if you're using an IGBT or silicon carbide FET, I think for this case, the first thing is really understanding your driver's ratings on the output. I have is my output stage on the driver capable of handling such system? I think for the UCC 21520 case, that's a possibility. I need to double check on that. I'll get your information and we can follow up on this, because I don't have a specific answer or a short answer on that. If we can reach out after this meeting or via E2E.
Yeah, I think E2E would be, I think E2E makes the most sense. I'll post the link to E2E in the chat, Mamadou.
Perfect. Thank you.
Does anyone else on the line have any more questions they want to ask in the chat? For reference, like Mamadou was talking about, I just posted the link to TI.com's E2E page. If you have any follow-up questions from the session, feel free to post them to E2E, and they will get routed to our team to help answer. And I think that's it for questions. So I just want to say thank you, Mamadou, for the great presentation, and thank you for everyone that joined us today. I hope everyone got something out of the session, and I hope the interactiveness was helpful to everyone's learning. All session recordings and presentations will be available later this week on ti.com/high-voltage-seminar, and everyone will also receive an email with links to the on-demand presentation and a post-event survey. So we would definitely like everyone's feedback so we can keep improving our content. So thanks again, everyone, and I'll let Mamadou close this up.
Thank you, guys. Thank you. I appreciate your time and help. Very good interactive session. Good questions. Hopefully, we can build on this and help you guys with your need with gate drivers. Thank you.